Okay, we're going to move on to Gert Kouwenbergs. Gert is professor of bioengineering and co-director of the Institute for Neural Computation. He's going to speak on reverse engineering. I'm somewhat freaked out by this title, I'll have to say. Reverse engineering the cognitive brain. Having dealt with a society that has done a lot of reverse engineering, and obviously in a very different way.
Yes. Thank you. So, yes, I guess I'm the oddball here as an engineer, but so in fact we'll connect with many disciplines here. That's the whole key here of our workshop. So it's a very exciting time for neuroscience. In fact, not just for neuroscientists, but for all of us. Scientists, engineers, artists, humanities, and really it's all coming together. It's quite amazing if you think of it that even Washington is fully aware that the brain is important, that we have to really study it and understand it, and that President Obama is completely behind it. This is in the forefront of the agenda. In fact, we owe it to some local champions here, so Nick and Ralph really championing this in Washington. And also Teresinovsky, whom many of you may recognize here at the right hand of President Obama. Right, so, and what is this about? So why does it take all of us to engage in this activity, right? So why can't a single discipline do it? Well, it's just so complex. The brain is so complex, involves so many levels of scale, down to molecules, I guess single elements, atoms even if you want, or ions moving in solution, all the way up to the brain as a whole. And the brain as a whole, of course, interacts with the environment, right? Interacts, because in terms of movement, it does things, but also it interacts socially, and that's also what we hear talking about today. So those different levels of representation require a vast set of tools and approaches. And neuroscientists typically have delved into the details of ion channels, I guess synapses, neurons, all the molecular scale of things. And now the Brain Initiative is really pushing this up and extending the scale to that of eventually the whole brain, millions of neurons, etc. Right? So that's all very exciting. But from an engineering perspective, it's also quite exciting to go the other direction. So scientists typically analyze, whereas engineers synthesize. Right? So go the other direction and build brains up from the bottom up. Right? So that's because in the words of Richard Feynman, if you can't build something, you haven't fully understood it. So, and that's a major an endeavor of neuromorphic systems engineering. And once we're at the level, once we're able to build those brains, or something that looks like a brain, then it becomes also exciting from a perspective of computational neuroscience. We can emulate very large models, and we can also study brains and behavior on a very large scale. So then it becomes interesting for all of us, including humanities and arts. Right? So that's can get quite exciting. But what it started here is this concept of neuromorphic engineering in a way that shows that we have this extension, physical extension, of some of the foundations of the physical origins of computation in the nervous system, then all the way to similar mechanisms, isomorphisms, into then circuits and silicon. So Carver Mead showed that the same mechanisms of transport, ion transport, that you have through ion channels, through membranes, also apply to transport of electrons or holes in silicon. And so immediately the idea that started here is, well, can we now build in silicon physical elements of this neural computation down from the starting ion channels and up to circuits and then eventually to the whole brains. And it has been a very exciting journey over the last 30 years. So here's an example of some early work where we actually take where we physically morph than what we know in neuroscience in terms of the circuits, the underlying circuits, and then some of the elements, photoreceptors, synapses, etc., neurons, and then build circuits that really implement those at the physical level. And here's an example of a circuit that had, say, a few hundred pixels. Of course, today, several years later, we can do now millions of pixels because modeling larger systems for cortical computation. And here's some other examples of systems that would show You can even go down to the spiking level and understand, say in this case, what the optic nerve is doing. You can observe some of the activity. It looks a bit grainy here, but I can actually quite, it's amazing what we can see through our eyes through this very noisy representation that goes through the optic nerve, just spikes. And the fact is, we can have this amazing capability of seeing through this very noisy representation. So there is definitely something to it that it will be important for us to explore from a computational point of view, right? So how does it all relate to cognition, right? Where does cognition in this, let's say, studying the visual system, right? So what is so important in cognition? So in cognition, you're dealing with a task, something you have to solve. A problem can either be defined explicitly, in a search case here, if you're doing search for a given task. Of course, cognition is more than that. There's also intent, and there is also reward, and all that can modulate intent and free will and that. But so in a particular task, a search task, there's a problem of complexity in that the task complexity induces large machine complexity. If you want to search for something in a scene, and you want to give a perfect answer, you just have to go through all the possible cases. You have to explore the entire state space. And digital computers really have a hard time at this in that the complexity scales quite dramatically with the complexity of the task. Neuromorphic engineering then aims at an alternative means for solving these hard tasks by abstracting complexity into simpler representations that make use of this collective analog imprecise, but gives collective computation that allows them to outperform on those techniques. Because simply it's impossible to solve hard tasks with these digital techniques, but then this analog graded techniques that are more aligned with the brain and allow us to then make progress here and build something closer to what the brain is doing. So that's the premise. But the key here for making this happen, where the complexity then becomes more constant, where the machine complexity becomes more constant in function of task complexity, is the advantages here only occur or will be prominent for problems with high task complexity, which also infer this quite relatively high machine complexity. You won't be able to solve a hard task that humans can solve unless you have the complexity of at least what the human brain has in store. So there are two aspects of this that are important. One is we have to, in order for neuromorphic engineering to get at a cognitive level and actually do something real, we need to, first of all, build systems that have a level of complexity in terms of power, in terms of synaptic connections per second of the human brain. And also we need to then be able to abstract from the environment enough knowledge through learning that can abstract the representation of the world into this reduced representation, which actually is still very complex, 10 to the 15 synapses, right? So there's a problem here of deep learning. And the great thing here is that such endeavor encompasses all the different disciplines that you have here, because in the room, and there's definitely engineering involved here, nanoscience, also cognitive science, because how you train the systems, but also humanities and arts, and right. So there are issues that I won't go into, because, but there are definitely very important aspects that also can be addressed here at all the different scales, right? And so we have now systems with millions of neurons, billions of synapses, right? So I'm not going to go into too many details here, but so it gets very exciting in that we can start building the systems up with resources we have here, the supercomputer center, et cetera, to make this really a community-driven effort and resource for simulating very large-scale networks. And using some of the advanced nanotechnology out there, including phase-change memory, what will be going in the next generation of memory that you have in your cell phones, we can build these very large arrays of synapses, emulating then these very large networks that are important. And we can integrate all this with CMOS, standard CMOS circuits, standard silicon circuits, to then build these very large-scale networks. Not quite 10 to the 15 synapses and 10 to 12 neurons, but we can get close to that because sooner or later. And power is also extremely important here. So power can be then, right, so now we have systems that operate at femtojoules per synaptic operation, which is actually on par with the human brain, of course, with all due respect that the brain is doing much more than just accumulating information, because with synaptic connectivity, you can also train the systems, right? So we're putting things together, so at the level of behavior, so where we couple those neural systems and studying then the brain, interacting with the environment, right? So then we can start asking questions that really touch upon our lives and social interactions using different modalities of what's involved here. But so the key here is that so we have this community here, and INC, Institute of Neurocomputation, is one of the organized research units, right? That is active at connecting across different disciplines, in this case for neurocomputation, making bridges on campus, right, to really pull together then the different disciplines involved here on campus, but then also because in the larger community, right, so making connections then with local companies and globally for really advancing then this arts and science of neurocomputation into the real world. So, thank you.
Okay, we're going to move on to Gert Kouwenbergs. Gert is professor of bioengineering and co-director of the Institute for Neural Computation.
Yes. Thank you. So, yes, I guess I'm the oddball here as an engineer, but so in fact we'll connect with many disciplines here. That's the whole key here of our workshop. So, it's a very coming together. It's quite amazing if you think of it that even Washington is fully aware that the brain is important, that we have to really study it and understand it, and that President Obama is completely behind it. This is in the forefront of the agenda. Exciting time for neuroscience, in fact, not just for neuroscientists, but for all of us. Scientists, engineers, artists, humanities, and really, because it all comes.
He's going to speak on reverse engineering. I'm somewhat freaked out by this title, I'll have to say. Reverse engineering the cognitive brain. Having dealt with a society that has done a lot of reverse engineering, and obviously in a very different way.